Hey everybody, welcome to the last episode of Open Space until I come back from hiatus. So the last episode of Open Space for this season. Not that I really have seasons, but still. So for those of you who don't know, I know I've talked about this before, but this is it. This is the final reminder. I go on hiatus with all of my live stream stuff. So the weekly space hangout, astronomy cast, open space, and the virtual star parties. They all go on hiatus for 2 months, July and August, and that just gives me and the team a chance to refresh, come up with new ideas, run experiments, and to be able to just do things that don't require a high-speed internet connection every day and a half. And I can't go anywhere. I can't do anything because I always have to make sure that I've got a high-speed internet connection. I'm lugging around technology everywhere I go. So it's good. It's good. It allows me to just relax a little bit. But that is not the end of what we're going to be doing. We've got big plans for the virtual star party. Now that we've gotten back in the swing of things with the virtual star parties, the plan is to get a much better planetary rig going and then go after some pretty cool targets. And so I want to expand that. And so we're going to be running a bunch of tests over the summer, both here on YouTube, but probably also on Twitch. I don't know. I feel like Twitch is a good place to do things that just disappear into the ephemera. So I assume I'm going to be doing some stuff on Twitch as well. The Guide to Space episodes are going to happen normally. The question shows are going to happen normally. The newsletter is going to come out like clockwork every Friday. So all of that stuff is still going to happen. It's just the live streams that we'll be taking a little bit of a break of. And then you should enjoy your summer. Don't watch YouTube, Twitch, Twitter, any of that stuff. Go outside, enjoy the sunshine, have a good time. Socially distant, of course. All right. A couple of you are noting the last night's star party was fun. It was a really good time. We got just a glimpse of the summer constellations, all of the cool summer nebulae, the Lagoon, the Trifid Nebula. Right by the end of the show, it was great. I think the best picture of the night was the shot that I took of the Lagoon Nebula. Although a lot of the other astrophotographers were sharing some pretty amazing pictures. Actually, I really liked Stewart's Cocoon Nebula. Anyway, so that's what we're doing this summertime. But now it's time for you to tell me what we're going to be talking about today, because I have no idea. Neil Yu asks, what percentage of black holes are dark matter, and what does it mean versus a pure regular matter black hole? We don't know what dark matter is, so it doesn't make sense for us to say what percentage of black holes are dark matter. However, it's believed that, say, 70% of the universe is dark matter. Therefore, it makes sense that 70% of the mass that's gone into a black hole is dark matter. However, as I mentioned in a recent question show, dark matter doesn't seem to have the same kind of cross-section that regular matter has, so it doesn't bump into itself in the way that regular matter does. And that's really important because you've got this accretion disk that is going around the black hole, and all the particles are bouncing into each other, and they're slowing each other down, and that's what creates that accretion disk whirlpool that goes in. And you sort of imagine when you pull out the drain on your bathtub and the water starts to swirl around. How come all the water in your bathtub doesn't just disappear right away the moment you've opened up the drain? Because the drain only has so much space that it can hold at any one time. And so the bathtub drains out, and it's the same process, except it's a black hole and it's the dead stars that are orbiting around it. And so once things cross the event horizon, it no longer makes sense to refer to them as what they were before they crossed the event horizon. Are they matter? Are they energy? Is it antimatter? Is it dark matter? It doesn't matter anymore. It's just black hole. And think of it this way. We know, according to Einstein's relativity, that E equals mc squared. So if you've got an amount of energy that's equal to the mass times the speed of light squared, those two numbers are interchangeable. If you take a kilogram of mass, it will turn into some enormous amount of energy. And if you take an enormous amount of energy, it'll turn into a kilogram of mass. If you take a kilogram of antimatter and a kilogram of matter, you put them together, you will get an amount of energy equal to 2 kilograms of mass turned into energy. All of that math just goes into the black hole? Is it, could you tell the difference between a black hole that is 100% made of matter, 100% made of antimatter, 100% made of energy? No, they're all the same. And what part of them is going to be dark matter? We don't know, because it all depends on what dark matter is, and we don't know what dark matter is yet. So until then, it doesn't make sense really to try to figure out what percentage of it is. People are saying that my audio level's a little low, but it's just me. So let me see. So I'm set as mono, and I'm going to shift it to stereo and see if that makes a difference, but it shouldn't. It's one or the other. It should be mono or stereo. So you're gonna have to tell me whether or not that worked for the audio level, Paranar. Forward Synthesis asks, why are Mars Trojans so stable compared to the recently discovered Earth Trojans that will be lost on short time frames? The mass that you can have in the Trojan field is compared to the mass of the planet. So the mass of the so say Jupiter, right? So you've got the sun and you've got Jupiter and you've got the Trojan asteroids. And these are these clouds of asteroids that are trapped in the L4 and L5 Lagrange points around Jupiter. And because Jupiter has an enormous amount of mass, the size that you can have these asteroids be is much larger. They can be hundreds of meters across. Earth is much less massive, and therefore the size of object can remain stable within its Lagrange point is very small. But it's not like things are just sitting at the Lagrange point. The Lagrange point is a hollow that objects are in that hollow, and they are orbiting around the center point, but it's not like they're just all clumped up at the very bottom of this gravity well. And so I'm not sure that the Martian Trojan area is more or less stable than Earth. It all depends on the individual specific object. If you have any one specific 5-meter asteroid that happens to be perfectly positioned at the bottom of the L4, L5 Lagrange point around Mars, it's going to be very stable. Same thing with Earth. But there's like only a handful of objects that have ever been found around Earth's Lagrange points. And I don't know how many objects have been found around the Martian Lagrange points. In fact, now I want to look this up. For the Mars Trojans, like any? Let's see how many there are. There are 10. So, and a lot of the thinking is that the Trojan asteroids at Mars came from whatever event caused Phobos and Deimos. And so you can imagine something smashed into Mars, blew out all of this debris into the Martian sun leading trailing orbit, like this sort of, material in front and behind Mars. And then some of that could have interacted and gone into this Lagrange area and then got stuck in there. But, all right. Bobby Reynolds. So what if you throw a fire at a black hole, and do you think the only reason how to defeat a villain as possible as Galactus is to throw them into a black hole? Yeah, I mean, if you took Galactus and you put him into a black hole, the black hole would eat Galactus. Like, assuming Galactus is made of universe stuff, then he can't, unless Galactus can go faster than the speed of light, which I guess he can, because he goes from star system to star system and eats them, and he doesn't do it in hundreds of thousands of years. He does it fairly rapidly, so he can move faster than the speed of light. But even so, even if you can move faster than the speed of light, you're going to go into the black hole. All roads lead to the singularity once you cross the event horizon. So as long as Galactus stays outside of the event horizon, since he somehow can move faster than the speed of light, he should be fine. But if any part of him gets touched by the event horizon of the black hole, then that part is going to be part of the black hole from here on out. Throw fire into a black hole, that's just energy. And so energy goes into a black hole, no problem. It just makes it a more massive black hole. Arjun, what is the likelihood of any coronal mass ejections hitting Earth? Have there been Carrington level events that missed Earth? Often. Yeah, it seems like so a coronal mass ejection, or just like Carrington level. So back in 1859, telegraph workers, well, people around the world saw auroras from the poles to the equators, which is not a thing that you normally see. And that's because an enormous, extremely powerful solar flare event interacted with the Earth's magnetosphere and atmosphere and created this enormous auroral display. And it was so powerful that it lit telegraph poles on fire. It essentially pushed electrons back and forth along telegraph poles and lit them on fire. Imagine what an event like that would do in the modern times. And the last time that we had something that was kind of like that was back in the 1990s in Quebec. There was an ice storm, and at the same time, there was a horrible solar storm that took a ton of the electrical grid offline. Quebec is fairly north, and so it got a direct hit from the charged particles hitting the Earth and caused a problem. Astronomers have seen Carrington level events blast off the sun in the past. It's just that they weren't going towards the Earth. And it's now thought that we get fairly significant solar storms striking the Earth more often than we ever believed. Probably somewhere on the order of about every 30 years or so, 30 to 50 years, a damaging solar storm. And so the last one was that one in Quebec, and there have been other less damaging ones. But you can kind of anticipate a fairly devastating solar storm to strike the Earth every couple of decades, which is kind of scary. We are so not prepared for the next solar storm. Okay, Horizon Brave. So pulsars are neutron stars that have their jets pointed towards our vantage point, right? So if a pulsar moves, does it get downgraded to just a neutron star? So with a pulsar, we're not actually necessarily getting the jets pointed directly towards us. We're seeing the jets a little from the side, but just every time the jet is moving in roughly our direction in our hemisphere, then we see the pulse of radio emissions coming from the pulsar. The thing that turns a pulsar into a regular neutron star is just age. So when a supernova goes off and it explodes, you're left with a rapidly rotating core of the star itself. And it's going very, very fast. It's buzzing around, spinning like a top. And that is because you've got this conservation of momentum. All of this mass from the star exploded, imploded down, and the whole rotation of the entire star is now captured in this tiny little object, and it's buzzing really quickly, spinning around and around, hundreds of times a second. It's insane that an object with that much mass can spin that quickly, and yet it does. So over time, as it's spinning, as it's releasing energy, it's also releasing gravitational waves, and that is causing it to slow its rotation down. And over time, over millions of years, the thing slows down so that it no longer becomes a pulsar. Right at the earliest moments after a pulsar forms, it's buzzing around so quickly. It's got this powerful magnetic field, and it's twisting and turning and spinning around its local environment. And that seems to contribute to the amount of radiation that we're seeing. But then when it slows down, then after a while, the whole environment settles down. And that's why we see pulsars at different rates. The faster a pulsar is spinning, the younger it is in general. Tesla Ranger. What is the difference between a conjunction and a close approach? In the Sky uses both, and they're at different times. For example, the Moon and Jupiter on July 5th, a conjunction at 5:38 Eastern Time, and a close approach at 5:56 Eastern Time. I don't know the difference between specifically a conjunction and a close approach. A conjunction between planetary objects is when they are very close visually in the sky. And the classic example, I'm sure you remember this a couple of years ago, there was a time when Jupiter and Venus were really close together in the sky. And it's so funny when that happens. I always love to watch Twitter. People are like, how come I never noticed those stars before? And you're like, because they're not stars, they're planets, and you're not paying attention to the sky. That's why. The rest of us have been waiting for this moment. But when they get close in the sky visually, that's called a conjunction. And we see conjunctions of different objects at different times of the year. The one that I'm most excited about, the one that's coming up in, man, I always forget the date, but I think it's in December 21st. Anyway, at the end of this year, Jupiter and Saturn are going to be so close together that you can see them both in the same field of view in your telescope, which is going to be just incredible. That you're looking through a telescope and you're seeing both Jupiter and Saturn at the same time. You're seeing both their moons. It's going to be amazing. I think it's going to be one of the biggest events of the year, and people aren't ready for this, but it's this year. So be prepared because we're going to freak out about it. So what is the difference between a conjunction and a close approach? I don't know. Semantics? I mean, conjunction, there's no real rough reason why when you've got a conjunction, like how close is it that it's worth noting? Different people have different opinions about that. So I don't really know what the difference is between those things. Horizon Brave says, what happens when the pulsar slows down? What happens? Well, so it just runs out of the magnetic field, settles down. It no longer pulses out the radio waves, and it just slowly rotates, emitting radiation based on its temperature. And that's a neutron star. So you only get the pulsar stage. It's just that beginning stage after the thing explodes. It tells you that the thing is new. It is a supernova that went off in recent memory. I don't know the exact number of how long ago. I need to stick this into my brain. So, question from William Beckham. If a massless object could exist, would a black hole have any effect on it? Sure. There is a massless object, the photon. It exists. Black holes absolutely have an effect on it. And remember, gravity does not work by things with mass sucking them like a vacuum cleaner, pulling them in. It's not how gravity works. Gravity is actually a distortion of space-time, and things think they're following a direct line. The moon thinks, if you can say that the moon thinks that it's going in a straight line, but actually it is following the curved space-time around the Earth. And the same thing happens with light. Light follows a curved space-time as it passes by objects with a lot of mass. And black holes have a lot of mass. They curve and distort space-time so that all roads lead into the black hole. And so it's not that a black hole, but you could have a photon of light orbiting around a black hole. No problem, perfectly balanced, not flying away out into space, not falling into the black hole, just orbiting around and around and around. Martin Van Vick, love your vids. When we go out in the universe, we see as it once was in the past. 1 million light years away is that many years ago. Would this not be possible to hide alien civilizations? We have no way to see what's happening in the universe now. Yes, when we look out into space, we are seeing the universe as it was, not as the universe as it is. We see the sun, it's only 8 minutes ago. We see the moon, it's only a second ago. We see Alpha Centauri, it's 4.5 years ago. We see Andromeda, it's 2.5 million years ago. Each one of these situations, we are seeing into the past. And so, yeah, absolutely. If we are looking across the Milky Way, we are seeing, say, the Milky Way is, for us to look to the core of the Milky Way, it's about 27,000 light years. To look out into the outer edges of the Milky Way, it's about 30,000 light years. And so if there was some civilization that was, say, 10,000 light years away, which is perfectly feasible, then we would be seeing what they were up to 10,000 years ago. And so, yeah, we are not seeing, if we do see some alien civilization on some world 1,000 light years away, we are seeing what they were doing 1,000 years ago. But that's still fine. That's still great. We at least get some kind of hint that there was life in the universe 1,000 years ago. And you take a snapshot of the Earth at any time in its history after life got started, any 1,000-year snapshot of life on Earth is going to be roughly the same. Any 10,000-year snapshot of life on Earth is going to be roughly the same. Even every million-year snapshot from here to Andromeda, it's going to be roughly the same. I mean, some new species, but there's going to be plants, there's going to be oceans, there's going to be clouds, there's going to be things are going to be mostly as they were. And so when we look out into the universe and we do detect some kind of evidence of an alien civilization or something, we will definitely want to remember, and no one will ever let us forget this, that we are seeing them as they were in the past. And so if we see them in some state of technological advancement, maybe they're in a pre-industrial civilization, but we're seeing them 1,000 years ago, then they've had 1,000 years of progress since we saw them 1,000 light years away. And that's fine. I mean, like, that's the best we can do. To know that there was once life would be good enough, I think. And when you go back to this idea of the Fermi paradox and how you would expect to have civilizations that would be expanding from star system to star system across the entire galaxy, that would have taken about, say, 10 million years to be complete, from no matter where in the Milky Way a civilization starts. They start in one corner of the Milky Way, they build a bunch of robot probes, those probes go to the next place, they spread, they go to the next place, and after a while you have taken over the entire Milky Way. And we are part of the Milky Way. And so the question is not, why don't we look out into the Milky Way and see other civilizations far away? Why don't we hear the signals that they're sending across? The question is, why don't we see monoliths here in the solar system? Some kind of concrete evidence that there was an alien civilization here in the past. Their robotic von Neumann probes came through, built the monoliths to say, hey, we were here. When you get your technology to a level that you can go to your moon and you can find the monolith, then here's the instructions on how to build a warp drive. Join us when you're ready. That's a thing that we don't see. There is no evidence that we have seen at all that any other civilization has ever passed through this region of the Milky Way ever. And so that's the part that is so confusing. Nifty. Can you build a Dyson swarm around a black hole and then dump the infrared radiation into the black hole to remain hidden from the civilization eater? If you are going to use heat, if you're going to use energy, then you are going to be releasing heat. And although you could try to direct some of that infrared radiation towards the black hole, the emitters that you're using to direct the infrared radiation towards the black hole is going to be emitting infrared radiation. So there's no way around giving off any kind of heat signature at all. I know that's the goal, is to minimize the heat signature, but there's only so far you can go until you actually do have to let that heat escape out into the universe. Even if you've got a pet black hole. The black hole, like if say you're using the Penrose process with your black hole, you're dropping matter into the black hole, it's being torn in half, you're catching half of the matter as it speeds back out of the black hole, you're converting that into energy, that's going to release heat. You're taking as much of that heat, you're storing it, you're directing it with infrared radiation back towards the black hole. That energy direction machine is releasing heat. So you will always be releasing some amount of heat. You can get pretty clever, I'm sure, but at the end of the day, you will be releasing heat and it will be obvious. Mike Mason, do we transfer life to other bodies in the solar system on our spacecraft and rovers? That's the worry, is that we do, that we have not done a great job of cleaning all of our spacecraft as they've gone to other places. And we are learning more and more that there are environments that seem to be quite positive for life. The under ice oceans on Enceladus and Europa, like some of the underground water sources that seem to be maybe on Mars. So each one of these places is a risk, and the thing that we're learning about Earth life is that it is very, very hardy. It can handle extreme conditions. It can handle going to space. It can handle the radiation, the dryness, the lack of atmosphere, the temperature, all that. It can handle that. Cyanobacteria. There's a bunch of life forms. We've done a few videos on this. There are a couple of life forms which you take to space, you fly to Mars, and then you land on Mars, and they not only could start growing again on Earth, but they can start growing on Mars. So we're really learning that we have forms of life here on Earth that are just ready. They can't wait to get their little tentacles on Mars. And so we have to be super, super careful about this process. And that's why Cassini was smashed into Saturn at the end of its life. That's why the Galileo spacecraft was smashed into Jupiter at the end of its life. There's just one less chance that our filthy Earth life can infect one of these alien worlds. Forward synthesis. So it would take a lot longer if the robot probe started in Andromeda, though, wouldn't it? Yeah. I mean, if the robot probes started in Andromeda, then you're looking at then each galaxy is going to be completely settled by the spacecraft. And then the spacecraft are going to make this long journey between galaxies. But it's not like you just have to go directly from the edge of one galaxy to the edge of the other. It's probably going to be star systems, dwarf galaxies, all kinds of stuff in between the two galaxies that you can hop from place to place. In fact, the thinking goes that once we do a better job of mapping out the Milky Way itself, we're going to find that the trip for us to make is not from here to Proxima Centauri. The trip is to get from here to the countless rogue planets and brown dwarfs that are in between us and Proxima Centauri. There could be tons and tons of objects that are littered throughout the Milky Way that we just can't see very easily. But once we do a better job of build bigger telescopes, more sensitive, we can start finding them and use them as way stations as we go. And so again, if we were going to imagine that we would be traveling between galaxies, it still seems feasible that even if the Andromedans, let's say they took, so let's say it's going to take 2.5 million light years. Say they go 10% the speed of light, hopping from place to place. So it would take them 25 million years to get from Andromeda to here. It would take them 10 million years to colonize all of Andromeda, and it would take them 10 million years to settle all of the Milky Way. So that's 45 million years for an advanced civilization to show up somewhere in some tiny little corner of Andromeda until it has not only settled all of Andromeda, but all of the Milky Way and all of the dwarf galaxies that are around us as well. So it will have gobbled up the Sagittarius dwarf galaxies and the large and small Magellanic Clouds. They will be filled to the brim with civilizations as well. 45 million years, although it's a long time, like that's when still almost to the time of the dinosaurs, it's not long in the age of the Earth. It's not long in the age of life on Earth. Life on Earth has been around for billions of years. Multicellular organisms have been around for 500 million years. Oxygen has been present in our atmosphere for that long. So even crossing the gulfs between galaxies is not too far. Our Instro is asking, hey Fraser, will you be doing anything for the CosmoQuesticon in July? Yes, I will. So if you don't know, the CosmoQuesticon is going to be an online convention that's happening, organized by my good friends at CosmoQuest, and I will be participating. I'm not sure how yet, but generally, whatever Pamela plans, I am brought into to help out, and so I'm sure I'll be part of it. I just don't know what I'm supposed to do yet. Noob pilot, might be a silly question. Do black holes emit heat through some thermodynamic process, or is heat simply a form of radiation that can't escape it? Black holes themselves don't emit any radiation because, again, the escape velocity from a black hole is faster than the speed of light. Therefore, nothing can escape a black hole, not even the radiation that's emitted by the black hole. That just goes back in, so nothing gets out. Now, I know a lot of you are saying, but what about Hawking radiation? So in theory, the region around the event horizon of a black hole does emit some radiation through the interaction of the black hole and the virtual particles that exist across the universe. And that is perceived as heat. And so you would see a black hole would have a temperature like a black body temperature, a very cold temperature, but it would have a temperature, and that comes from the photons that are being emitted right outside the event horizon. And of course, as those are emitted, they take away from the mass of the black hole itself. But the black hole itself does not emit any radiation. It's not possible. It doesn't emit anything. Nothing comes out. Visto Tutti, does the Big Bang violate known physics? So much matter in a dense state that should collapse in down, or speed up at all. Mixed a couple of questions there. Weird. Hold on. Okay. Visto Tutti, does not the Big Bang violate known physics? So much matter in a dense state that should collapse into a black hole. Why expand? So to get a black hole, you need a overdensity of matter in some region, surrounded by an underdensity of matter in other regions. And of course, in your mind, the thought is, okay, you've got this black hole, you've got the beginning universe, the singularity, whatever it is, and it's this ball, and then it expanded, but it has more matter, more densely compacted down than a black hole does. So how could it even expand? Why didn't it just go and crunch back down together again? Well, I don't understand. And people always ask some variation on this question, which is, why didn't the Big Bang just become a black hole again? And the answer is that there's two parts. One is, there's no reason to believe that the universe was a ball, that it could very well have been infinite in all directions, even at the beginning. It's less dense today, it was more dense in the past, but it might be infinite today, and it was infinite in the beginning, even though it was more dense. In other words, if you just had particles, the particles were more closely packed together, yet it was still infinite in size in all directions, and then everything expanded. But the other part is that you need this overdensity. So the only way you're going to get a black hole is you've got a whole bunch of mass that is pulling itself together into this one black hole. But if you've got all this mass fairly evenly spread across the entire, maybe infinite universe, then there's no part that the mass can be pulling together, because it's all also trying to spread apart. And so it wouldn't turn back into a black hole. Staring at the binder. Still don't understand Hawking radiation. Half of the virtual particles fall in. Wouldn't that make black holes more massive? The point with Hawking radiation is that we see photons of light coming from the black hole, from the region around the black hole. And you can't have energy just appear in the universe. Therefore, something has to pay the price to allow those those photons, those heat particles to appear, the photons of heat. And the thing that has to pay the price is the black hole, the mass itself of the black hole, in theory. Although, Hawking radiation has never been actually seen. So this is just the way the math works. Jameson 1776. Fraser, I know your thoughts on alien civilizations, and I most agree with that being said. Do you believe that humanity will one day colonize other star systems biologically, or are AI descendants? So my fairly controversial opinion on the Fermi paradox, why don't the universe is big, old, aliens should be everywhere, we don't see any, why is that? The answer that I personally feel, and I wouldn't say it's controversial. I mean, most of the scientists who think about this, most of the people who've done a lot of research on this, it just seems impossible that if there was life anywhere, it should be everywhere. And because it's not everywhere, it's nowhere. And so my opinion, my gut, is that we're alone in the universe. That if there was even one intelligent civilization somewhere, or a couple, then they would have colonized the entire Milky Way. And the fact that we don't see that means that they don't exist. But but and partly that's because I think that we will go on to go everywhere in the Milky Way. That either we, and I don't think it's going to be us, but definitely our robot overlords. Once we invent general artificial intelligence, once the artificial intelligence rises up, destroys all humans, it will then go about going to every corner of the Milky Way because it's going to want more mass and more energy for being able to do computation. So, yeah, I do think that and every day that goes by, and every day that we are able to launch more things into space, and every day that we're able to make our computers work better, and every day that we're able to make 3D printers and learn all of this technology, it just seems more and more weird that we don't see anyone else doing this, because this is what we're going to do. We are on this path, and it's not going to take us long. 10 years from now, we will be seeing hundreds of rocket launches every day if Starship gets rolling. 50 years from now, we will see fairly sophisticated 3D printing happening in space, manufacturing and resource harvesting. 200 years from now, we will see a fairly serious presence of humanity, or it's the AI overlords, across this entire solar system. 1,000 years from now, we will have sent self-replicating robot probes to a pretty serious portion of the nearby Milky Way. And these numbers are all just a blink of the eye compared to the age of the universe and how long other civilizations have had to do this. So I know people say evidence of absence is absence of evidence or whatever. Every day that goes by that we get better at doing what we're doing, as we gain more control over space itself, it makes it weirder that we don't see anybody else doing it. 200 years ago, this thought never would even have occurred to us. And then rockets were invented. And then people were like, wait a minute, maybe we could fly to Mars. And then better rockets were invented. And then people were like, wait a minute, maybe we could fly to other star systems. And now we're making that true. And why haven't the aliens done the same thing? Dennis Tyrant, question: if our galaxy has a supermassive black hole, why is it so small for a supermassive black hole? Are you supermassive black hole shaming our galaxy, the Milky Way? 4.1 million times the mass of the sun. Is that not impressive? What makes you impressed? 1 billion times the mass of the sun? 100 million times the mass of the sun, like Andromeda? 1 trillion times the mass of the sun? 10 trillion? I mean, those are impressive numbers. It's just we don't know exactly all of the events that led to the formation and accretion of the supermassive black hole in the Milky Way. It just happened over time. It merged with other black holes. It collected gas. It ate stars. It had periods when it was going through active star formation, periods that it didn't. Maybe the Milky Way didn't have enough close interactions with other galaxies. But man, it's trying the best that it can. All right. Giro the Hero. Do you think that we will find simple life forms in the universe if there is no advanced civilization? All right. So this is where I probably diverge from a lot of other people, and I'm willing to more follow in the general understanding. Most people think that simple life forms are probably common across the universe, and complex life forms, multicellular life forms like us, are possibly more rare and maybe unique. That the only time the multicellular concept was ever figured out was here on Earth. Every other place out there, they never got past some kind of self-replicating single cellular organism, so you just never got anything more interesting than bacteria. That doesn't really hold for me, because I can imagine large amounts of bacteria working in ways that could start to simulate multicellular organisms. You can imagine a situation where a lot of bacteria in some kind of colony like ants are behaving in a more complicated way. So my feeling is that I don't think we're going to find life anywhere. I don't think we're going to find it on Mars. I don't think we're going to find it on Enceladus. I don't think we're going to find it. And if we do find it on Mars and Enceladus, then it's going to be related to us. But I don't think we're going to find life anywhere out there in the universe. I think it's dead and empty. And I know that's a bummer. And I know that's weird for me to say that and very controversial. But I just find the concept, the capability of this progress of life that has happened so compelling that it seems inevitable. And that feels to me like that should be playing out across millions, possibly billions of worlds across this entire galaxy. And all it takes is one to crack space flight, and then they have built monoliths on every corner of the Milky Way. And it's not like I don't think we should look. I think we should totally look. I think we should look our hearts out. We should look for thousands of years as hard as we can, because it is the most important scientific question that we can possibly ask. Are we alone in the universe? We need to find out, because the answer to this question is incredibly important, no matter which way it goes. If it turns out, and this is the classic Arthur C. Clarke quote, right? Two possibilities exist: either we are alone in the universe or we are not, and both possibilities are equally terrifying. If we are not alone in the universe, that's scary. It means there's competition out there, that it's like an ancient tribe in some corner of, I don't know, some part of Europe, realizing there are other civilizations around them that have different weaponry, and they're more advanced, and some of them are nice and some of them are mean. That's scary to learn that, to make that discovery about your neighborhood, that you're not alone, and you get to kind of go into every nook and cranny and enjoy the Milky Way to yourself. But in fact, there are any number of benign or hostile alien species out there, and science fiction has told us how this plays out. Human history has told us how this plays out. But the other possibility is that the universe is completely empty, that there is no other life except on this one planet, in this one backwards corner of this one galaxy, in this one cluster, supercluster. And the responsibility is on us to not mess this up, that we are the first and possibly only sentient civilization that has ever or will ever arise on planet Earth, the one place that life has ever shown up in this entire Milky Way. And we don't know whether we're going to pull this off or we're going to go extinct. And then intelligence will never arise again. And then the sun will cook all life on Earth, and then the sun will die, and then the Earth will die. And life could have had a chance, and it didn't. And that'll be on us. So either way, it's a compelling thought experiment, one which we really need to get to the bottom of. So we should look. Building with Todd, have you seen Cosmos? I haven't yet. Sorry. I'm sorry. Canadian sorry. T-Home, how much evidence does it take before concluding that we are alone? You can't prove a negative, but you can only gather a lot of evidence of a negative. Yeah, we can never know for certain if we are alone. We can either find evidence of alien life and then know that we're not alone, or we can just keep looking. And I think we should just keep looking until we are extinct as a civilization. Like we should keep looking and looking and looking. We should look in every wavelength, and we should look on every world, and we should use every technique, and we should build bigger telescopes. The question is that important to literally the future of the universe. Imagine if we messed it up and then there was just no life anymore in the universe for billions, trillions, quadrillions of septillion years. That would suck. Life is great. Life is fun. Life is cool. Life makes the universe a better place for us having been here. Even with all our faults, the universe is better with us. The universe is better with dogs and dolphins and even mosquitoes than it is without it. Dustin King, if life isn't common, what do you think makes it rare? Is it just too many things have to line up, or is it just something else? We don't know. I mean, the reason why I think that life is rare or unique is just because every time life gets a toehold anywhere here on Earth, it takes over. And so we would expect to see life taking over the entire Milky Way, and we just don't. That's the heart of it. Doesn't matter where it starts, it takes over. And we don't see life taking over. Therefore, in my opinion, there is no life to take over. Matt Potter, if the universe is expanding faster than the speed of light, doesn't this limit how far back in time we can see? How far back in time can we see? How long after the Big Bang can we see? All right. So the universe, parts of the universe from our perspective are moving away from us in such a way that they appear to be moving faster than the speed of light. And I know that was like me using a whole ton of weasel words there, but when we look out into the universe right now, we, in all directions, are able to see the cosmic microwave background radiation, which is the beginning of the universe. And so we are actually able to see the beginning of the universe in all directions. We're also able to see galaxies which are moving away from us that are theoretically moving faster than the speed of light. And as these galaxies go faster and faster and faster away from us, the wavelengths of light that we see coming from them are just going to get stretched out into the radio wavelength. And eventually they will just fade away to the background of the universe. And so in a few trillion years, there will be no evidence of the cosmic microwave background or that there were other large galaxy groups in the universe. It will look as if there's only the Milky Way, Andromeda, a couple of dwarf galaxies around us, and nothing else out there in the universe. Arjone, what makes humans intelligent? Is it that we can hold a thought for a long time, or maybe language or counting? No, I mean, every single thing that we seem to be able to do, animals seem to be able to do as well. And yet there's clearly something that humanity's got going that animals don't have. It's not technology. I mean, you can see crows using a stick to get to get food. You can see chimpanzees doing that. Animals can understand language. There's all kinds of things that we used to think was just the domain of humanity, and yet animals do almost every single little piece of it. But we put it all together into one package, and I think that's just the difference. We do something just in collection that just doesn't happen. Sereneth the Binder, what if we are the universe becoming conscious? Yeah, man, that's like cool. I love the Carl Sagan quote, of course, this idea that we are the way that the universe perceives itself. But I don't think that we have to describe the universe itself as conscious, just our little corner of it. Just right now, my brain is conscious. This part here, your brain is conscious. My son's brain over in the other room, he's conscious, but not the stuff in between, not the planet itself, not the open spaces in between stars. That's not conscious. Or maybe it is, I don't know. But I don't imagine the universe having some kind of collective consciousness itself. Let's see. All right, Nancy Graziano, hypothetical question. If two black holes could pass in close proximity to one another, one with 100 1,000 times the mass of the other, at a velocity such that they do not orbit one another nor merge into a larger black hole, but mass from the smaller black hole is sloughed off into the larger black hole, would it be possible for the smaller black hole to lose sufficient mass to the larger black hole that it no longer is a black hole? There is no way to slough mass away from a black hole. So those two black holes make a very close approach to each other. Either they're going to collide and become a more massive black hole, or they are going to narrowly miss each other and fly off into the universe. There's no in between. There's no way that even if the black hole, if one black hole just skims the event horizon, if the small black hole just skims the event horizon of the big black hole, it's going in. Because the only way that it could get away is if it could go faster than the speed of light, and that's impossible, so it's going in. There's no other way. But Nancy, thank you for everything. I just want to give a big, huge shout out to our good friend Nancy Graziano for all of her work and support and volunteer effort for all of the projects that we do. She is a superhero. If anybody is looking for an executive producer for some kind of space-related thing, NASA, are you paying attention? Nancy Graziano is the greatest. And I would suck to not have her help every week. But, yeah. Bill Nash, what are your thoughts on AI in control of spacecraft? A recent paper on using neural nets for burn controls caught my eye. It seems to be the way forward for deep space work. Yeah, you sent me that link, Bill. Right now, one of the big problems with exploration, using robotic exploration, is it's like a video game with a hour lag time. You know, the ping times to and from your rover take an hour. And so when the rover is very close, say it's just on the moon, it's very easy to do. When the rover is over on Mars, every little decision, every little thing that you want to do, you've got to go and you got to wait for the rover to move. You say, move forward 10 meters, and then you wait an hour, and the rover goes, I moved forward 10 meters, now what? And you're like, look at a rock. Which rock? There's your whole day. Right? And so it makes a ton of sense to get these things to start doing artificial intelligence. The rover drives around, looks at a bunch of rocks, goes, oh, that's the kind of rock that I know I want to look at, picks up the rock, examines it, does some scientific analysis, sends you back the data, says, change my code if you don't like what I'm doing. I'm just going to keep this up. You can imagine the enormous amount of science that would be coming back if the rover didn't need to wait for us. Same thing for spacecraft that are looking to make changes in their where they're flying with their thrusters. They should be able to make decisions about this kind of thing on their own, so that we don't have to give that back and forth, right? Spacecraft goes, I'm about to hit that asteroid. What should I do? Wait an hour. Dodge. No reply. So yeah, having your spacecraft able to make those kinds of adjustments make a ton of sense. And we're going to see mountains of that. Like, you could just imagine over the next few decades, we're going to see dramatic changes in the level of autonomy for various spacecraft. All right, Bobby Reynolds is asking, which of the two storms is bigger, the Great Red Spot or the Hexagon storm on Saturn? The Hexagon storm on Saturn is huge. It is a huge portion of the northern pole, but it is not, I wouldn't really call it it's not a single storm in the way that the Great Red Spot is a storm. It is a standing wave formation, which consists of a lot of smaller atmospheric features, while the Great Red Spot is one big storm. Sierra Vortex. Fraser, why are the new Star Wars movies so crap? I have not seen the newest Star Wars movie. I haven't been bothered. Like, I've had Disney Plus. I've been like, oh, there's the new Star Wars movie. Nah, I'm not going to watch it. I'm going to watch some weird Korean science fiction drama or something. So I don't know why you think they're crap. I just don't care anymore. Just like every part of me, every little piece of nostalgia that I have about Star Wars has just been mechanically, scientifically extracted and exploited and burned up. And the man you see today is just the shattered wreckage of that process. I have no nostalgia left. That said, Did you see the trailer, the new trailer for the Foundation series? Looks awesome. I can't wait. And I'm reading the Foundation books, and I was like, oh man, it'd be so cool to see the Foundation books done to TV show. And then I'm reading them, and I'm like, nah, you know what? No, they're not great. But now I saw the TV show premiere on Apple. I'm like, yes, please. So I want more science fiction. I want more science fiction stories like The Expanse or like Dune or like all this stuff turned into television shows. There's such a rich amount of incredible stories that someone has taken the time to think through and work it out. And all some TV company has to do is just take that plan and turn it into a TV show, however long it needs to be. And they're learning. Game of Thrones, like, there's money to be made here, and we will watch this. So stop making Star Wars movies. Stop making superhero movies. Take that money and make incredible science fiction, fantasy, speculative stories. The canon of science fiction is so rich and so deep. There's so many great ideas, and there are writers who you could make their day by buying the rights to their book. I would so much prefer that. One Star Wars movie could make, I don't know, a dozen cool science fiction, original science fiction TV shows more. What would you prefer? So I'm over Star Wars. Sorry. Let's see. Why are these Star Wars movies so crap? Man, 10-year-old Fraser would have none of that. I would be, I'm sure I'd be waiting for me to show up with a time machine and just have a stern talking with myself, because that was heresy for me to say those words. I never thought I would say those words, and yet I just did. Gwym, are there any proposed space missions to go really, really fast into deep space? No. There's no reason to go into deep space. There's nothing in deep space. It's deep. There's nothing there. It's just space. It's right there in the name. You want to go to places. You want to go to Titan. You want to go to Pluto. You want to go to the Kuiper Belt. You want to go to Mars, Venus. All of these things are destinations. And one of the side effects of going past an object like Pluto is now you're in space, and you can do space exploration, which is pretty boring. But no, there are no plans. I mean, eventually someone's going to take a crack at going to Proxima Centauri, but that's going to take a lot of energy. So until then, no, there's no plans to go just into space itself. Cole Maxfield, love your channel. How feasible is the Halo drive concept? I believe Dr. Kipping from Cool Worlds talked about it. Like, how feasible is it to harness a black hole as your space drive? Not very. You have to find a black hole. You have to be able to set up shop nearby it, be able to use the black hole as a source to power your spaceship. These things are not feasible. We don't. So, I mean, is it feasible? Does it defy the laws of physics? It doesn't look like it does. But just because something defies the laws of physics doesn't mean that it's feasible. It just means that it's theoretically possible. It's fun to think about, but you also have to hold in your mind, boy, it'd be really cool if we harness the power of black holes. And then on the second half, you have to hold the fact that we didn't have smartphones 15 years ago. And soon we're going to be having augmented reality, and soon we're going to have computers that are artificial intelligence are going to do all kinds of crazy things. So how we interact with the laws of physics is going to change depending on our situation, what humanity is. Tom Garcia, how do you find time to read Foundation and learn Chinese? Foundation books are not that big. You could read one of the Foundation books a night and be done in about 5 days. They're actually they're a collection of short stories. They're pretty small. The learning Chinese part has been brutal, but I'm making progress. Well, you know what? We've reached the end of our hour, so it's time. Time goes so quickly, and I know that this is the last episode before we go on our summer hiatus. So I just want to give you all a super duper thank you for all of your support, all of the people who have joined the Patreon, all the people who have come back every week and hung out in the chat, joined the star parties, joined all of the live shows that we do. If you haven't already, if you want to hear regular updates from me, make sure you join my newsletter. I know I talk about it every episode, but it's pretty great. There's no ads in it. It is the size of a small novel, a magazine, someone described it. I write every word, so it's my personality throughout the entire thing. And you are getting a really exhaustive breakdown of every piece of space news that's happened this week. So go to universetoday.com/newsletter to sign up for that. All right, so the last thing we've got on Wednesday is Dr. Andrew Simeon, the director of the Berkeley SETI Research Center, will be joining me and my co-hosts on the weekly Space Hangout, and then we're on hiatus. So, again, I couldn't do this without you. Thank you, everybody. It's so much fun to hang out and answer your questions, and I'm sure you'll see plenty of me over the summer. And if not, I'll see you in September. Thanks, everybody.